All right, so ready to dive into some deep learning?
Always. Image classification today.
Yeah, you could say it's a crash course in how computers see those cat pictures everyone's posting.
Or how about self-driving cars?
Yeah.
Recognizing those stop signs.
Yeah,
It's all connected, right?
it really is. And we're using Daniel Voigt-Godoy's book, Deep Learning with PyTorch Step-by-Step, as our guide, Chapter 4, Classifying Images Specifically.
Great choice. PyTorch is super powerful for this stuff.
Okay, so think about this. How would you teach a computer to tell the difference between a diagonal line and one that's like perfectly horizontal, all on a plain black background?
Sounds deceptively simple, but I see where you're going with this.
Right. It's like we instantly know the difference, but for a computer, it's all about the data, right?
Exactly. Computers see images as grids of tiny squares, those are pixels, and each one has a number for its color or how bright it is.
Oh, like a digital paint by numbers, but instead of colors, it's...
Numbers. And in grayscale images, it's even simpler, just one number per pixel, usually from 0 for black to 255 for white.
Makes sense. But color throws a wrench in things, I bet.
It does. Color means we need 3 values for each pixel, red, green, and blue amounts. That's RGB. Like stacking colored transparencies to get the full picture.
Oh, that's a good way to visualize it. But then there's this whole other thing, the shape issue. NCHW versus, what was it again?
NHWC. It's the order you arrange the image data in. Think of it like a burger. You got your bun, patty, cheese. Does the order matter?
Well, you could stack them weird, but
Yeah.
yeah, it'd be a different eating experience.
Same with computers. PyTorch likes NCHW, number of images, channels, height, then width. Other tools might use a different order. Guess speak their language.
So like trying to follow a recipe in a language you don't understand, recipe for disaster.
Totally. But thankfully, PyTorch has this awesome toolkit called TorchVision to help us out.
TorchVision? Is that like, I don't know, pre-chopping our veggies for this whole deep learning recipe?
Even better, it's got datasets, model designs ready to go, and tons of image transformations we can use.
Transformations, like giving our images a makeover before the big show.
Exactly. We call it data augmentation. Imagine teaching a kid about dogs, but you've only got a few photos. Data augmentation is like flipping those photos, rotating them, slightly changing colors.
So the kid still sees a dog, but learns to recognize them from different angles, different lighting.
Precisely.
Yeah.
Makes the model more adaptable. TorchVision has things like random horizontal flip, so during training, bam,
Yeah.
flipped images.
Clever. And does that apply to all data?
Ah, good point. Only to the training data. We want to see how well the model generalizes to new stuff so the validation data is left untouched.
So like a pop quiz, no cheating allowed. What about these other transformations you mentioned? To-image and toddy type.
Oh, those are essential. Remember how we were talking about data formats? They're like translators, making sure everything speaks the same language. To-image converts a tensor, think of it like PyTorch's way of holding data, back into an image we can actually see.
Like taking that paint-by-numbers canvas and turning it into a picture we can actually look at.
Exactly. And toddy type lets us change the type of data in the tensor, imported for certain calculations or when using different hardware.
Cool. So we've prepped our images, transformed them. It's like we're setting the stage for our deep learning model to steal the show. But before it hits the spotlight, there's more to this data prep than meets the eye.
You bet. Just like a chef wouldn't just throw ingredients in a pot without prepping them first, we got to get our image data ready for the main course. Think of it like this.
So we've been talking about pixels and data and transformations. It's like we've organized the pantry, prepped the ingredients. But when do we actually start cooking with this deep learning recipe?
That's where activation functions step in, my friend. They're the secret sauce, the special ingredient that takes those numbers and turns them into, well, intelligence.
Okay, so no more chopping veggies. This is where the magic happens.
You could say that. Remember how easily we can tell the difference between a cat and a coffee cup? Activation functions help computers do the same, but in their own way.
Right, because just stacking more layers in our model didn't really work, did it? It was like a fancy layered cake that all tasted the same.
Exactly. Those layers need something to make them learn, to see the patterns. And that's where these activation functions come in. They introduce something called nonlinearity.
Nonlinearity. Sounds complicated.
It's a big word, but think of it this way. A straight line can only show you so much, right? But real life, it's all curves and twists and turns.
So it's like our model was stuck drawing stick figures, but we need it to paint a masterpiece.
Now you're getting it. And just like an artist has different brushes, we've got different activation functions. Sigmoid, 10H, RALU, each with its own strengths.
Let's start with sigmoid. That one sounds familiar.
It's a classic. We've talked about how it squashes values, kind of like turning down the volume to keep everything in check. But importantly, it introduces that nonlinearity we need.
So instead of just seeing a jumble of pixels, our model starts to recognize shapes, edges.
Exactly. But sigmoid has a little problem. It can lead to something called the vanishing gradient problem. Imagine our model is learning, making progress, but the further back in the layers you go, the weaker that progress gets.
It's like a game of telephone where the message gets all garbled by the end.
Perfect analogy. Some layers aren't getting the memo to change and improve. That's where tan H comes in hyperbolic tangent. But tan H is way cooler to say.
So it's like sigmoid, but with a better signal.
You got it. It helps those gradients, those signals for improvement, travel further, keeping the learning process strong.
But you said it helps, not a complete fix.
You're sharp. For really deep networks, we often turn to ReLU, the rectified linear unit. It's a bit of a rock star in the activation function world.
ReLU. That sounds more like a superhero name than a math term.
Right. But it's super effective. Instead of squashing values, it just sets anything negative to zero. Sounds simple, but
it works. Why?
because it avoids those vanishing gradients completely, at least in those positive regions. Plus, it's computationally faster, which is huge when you're training big models.
So less work, better results. No wonder it's popular. But there's got to be a catch, right? Nothing's perfect.
You're right. ReLU can sometimes run into something called the dying ReLU problem. It's like, imagine a neuron in the network gets stuck, always outputting zero. Useless for learning.
Oh no, our superhero has a weakness.
Luckily, we've got backup. Leaky ReLU and parametric ReLU. They're like ReLU with a safety net, preventing those neurons from going completely silent.
Okay, so leaky ReLU, does it like leak information to keep things active?
In a way, instead of zeroing out negative values, it applies a small slope, a tiny bit of activity to prevent those neurons from getting stuck.
Yeah, and parametric ReLU, or PO that one sounds even more intense.
It's like leaky ReLU, but instead of a fixed slope, the model gets to learn the best slope for those negative values during training.
So it's like giving the model more control over its own learning. That's wild. But how do these activation functions actually work within the layers of a model? Where do they fit in?
Ah, great question. Imagine each layer as a step in a recipe. You mix ingredients, then what? You apply some heat, right? Activation functions are like that heat applied to the output of each layer before it goes to the next.
So they're not just in the layers, they're like between them, shaping how information flows.
Exactly. And just like the right amount of heat is crucial for a good cake, the right activation function can make or break a deep learning model. It's all about finding the right tool for the job.
All right, so we've got our ingredients prepped, our activation functions fired up. Time to build this deep learning model, right?
Time to bake that cake. And remember those simple line drawings, diagonal versus horizontal? Daniel actually tested different models on them.
Oh, yeah, to see how well they could tell the difference. Did just adding more layers help?
That's the thing. Just stacking layers without those activation functions, it didn't really make much of a difference. It was basically a glorified logistic regression, not true deep learning.
Why is that? I thought more layers meant more power, more learning potential.
It does, but those layers need the right kind of power. Think of it this way. Without activation functions, our models can only find straight lines, linear relationships.
Okay.
But real-world data, images especially, it's all about the curves, the nonlinear stuff. Activation functions like ReLU, they bring that curve-finding power to the party.
So they're like giving our model X-ray vision, letting it see the hidden patterns.
Exactly, and the results speak for themselves. The basic logistic regression and that deep-ish model without activations, they performed almost identically on those lines.
Really? So all those extra layers and nothing?
Yep, their losses were practically glued together no matter how much we trained them. But the model with ReLU activations, night and day.
So it actually figured out the lines.
It did. The loss dropped like a rock after just a few epochs, meaning it was learning way faster, actually understanding the difference. Those ReLU activations made all the difference.
Wow, that's incredible. It's like we gave it the right tools and it finally saw what we were trying to teach it.
That's the beauty of deep learning. And we've only scratched the surface here. Think about all the applications. Self-driving cars, medical imaging, even those filters on your phone. It's all image classification at its core.
It's mind-blowing when you think about it that way, and it all starts with understanding these basic building blocks, right?
Absolutely. Data preparation, activation functions, building those models layer by layer. It's like learning a new language, but instead of talking to people, we're talking to machines.
and teaching them to see the world. If you're feeling inspired to decode more of this deep learning language, definitely check out Daniel's book, Deep Learning with PyTorch Step-by-Step.
It's a fantastic resource, packed with insights and practical examples.
Well, that's a wrap on our deep dive into image classification. Until next time, keep those curiosity gears turning because the world of deep learning is vast and always evolving.